Modern physics is trapped in a conflict between two highly successful models. Einstein's general relativity treats the entire universe as a smooth, continuous fabric. Conversely, quantum mechanics describes the ultra-small as a series of discrete, probabilistic leaps. For nearly a century, physicists have attempted to force those quantum leaps onto Einstein's smooth, pre-existing stage. The two mathematical systems remain incompatible. The boundary condition quantum mechanics framework, or BCQM, resolves this paradox by deleting the stage entirely. At the most fundamental level, the vacuum is an illusion. There is no continuous cosmic fabric holding the universe together. To understand the true nature of reality, we must look past this illusion and zoom into the granular, underlying structure of pre-spacetime. Without a pre-existing background stage, the entire universe must be generated from the bottom up by a completely different mechanism. In the pre-spacetime void, reality consists of a single primitive building block, the event. An event is a discrete, irreversible quantum collapse, the moment a hazy cloud of potentiality solidifies into a single permanent fact. This illustrates the solidification process. Physicists call this horizon W, the point where a quantum system loses coherence and becomes part of the record. In BCQM, crossing horizon W represents the tick of proper time. Each pulse creates a permanent marker. This event generation moves strictly forward. The framework maintains a chronological axis that prevents backwards time travel or any influence from future choices. Every particle, object, and observer in our world is a sequence of these irreversible, microscopic ticks. Without a background stage to guide them, how does each new event maintain the precise order and conservation laws of the universe? The Q-wave serves as the information blueprint for this growth. It pre-filters every potential successor event to ensure that fundamental laws, like the conservation of energy and momentum, are perfectly preserved at the moment of selection. Sequential events link together based on that blueprint, forming a directed network known as the causal graph. This web constitutes the true structure of reality. Time, in this context, is the count of linked events along a specific chain. The speed of light, c, represents a strict structural limit of the network, the maximum spatial separation allowed per temporal tick. These fundamental constants emerge as organic, geometric properties of the growing graph, rather than arbitrary rules imposed from the outside. Scaling up by trillions of microscopic links causes the individual nodes to completely blur together, creating a solid illusion. The smooth 4D spacetime of general relativity is the statistical thermodynamic average of this massive underlying graph. Gravity manifests as the macroscopic curvature created when a high density of events alters local connection probabilities in the graph. BCQM provides strictly falsifiable predictions that distinguish it from untestable theories. If reality is a discrete graph, even perfectly isolated objects will exhibit a universal, irreducible random jitter. Researchers are searching for this inertial noise floor using high-precision laser interferometers. Astronomers are also monitoring the twin quasar Q0957+561. The framework predicts that the magnification of distant quasars should exhibit a continuous flicker due to the underlying graph's fluctuations. Evidence of this stochastic flicker would directly contradict general relativity's assumption of a perfectly smooth manifold. This active research program utilizes the James Webb Space Telescope and other next-generation observatories to hunt for these specific cosmic signatures. Finding these microscopic jitters and cosmic flickers would expose the pre-spacetime code generating our universe.